So we're in 16.1, but for some strange, I'll explain the reason why the book puts the homework in the chapter 7 section during the lesson. So, big picture, when we talk about a transform, what we mean is it's just some kind of operation that we do on a function that transforms it into a different function. So we could think of the derivative as a transform. We do this operation on a function and it gives us a new function. We could think of integration as a transform. We put a function into the integral and we get something else. And we know that the derivative and the integral are inverses of each other. But the idea of a transform is it just transforms a function into some other function. So I'm just going to say derivatives and integrals can be thought of as transforms. Derivatives and integrals have what we call the linearity property. Which is nice and very useful. That linearity property says that the transform of a linear combination of functions is a linear combination of the transforms. So for example, with a derivative, the derivative with respect to x of a f of x plus b g of x, there's a linear combination of functions, gives us a f prime of x plus b g prime of x. We get a linear combination of the derivatives. And it's the same with an integral. When we integrate a sum, we can break it apart into sums of integrals. That's what we call a linearity property, or we say the derivative is a linear operation or a linear transform. The integral is a linear operation or a linear transform. And we took advantage of that. We used that a lot when we talked about the superposition principle. When we had a sum of solutions, we talked about the derivative of each individual term. So today we're going to talk about a specific integral transform, the Laplace transform. So what we mean by an integral transform is that if we have some function of x and y, we know if we integrate with respect to one variable, we get a function of the other variable. With respect to one variable. We saw that a lot when we did multiple integration. If we have, we're going to form the integral from a to b of k of st f of t dt. So f of t is the function we're interested in. We're sticking it into this integral where k is some function of s and t. We end up with a function of s because we're integrating with respect to t and we have a definite integral. So we have transformed that function f of t into some function of s. If we are going to be working with an infinite integral, the integral from 0 to infinity of k of st f of t dt. And just as a reminder, this is the limit as b approaches infinity of the integral from 0 to b of k of st f of t dt. The book does some little abuse with the limit notation, just to be aware. I always write the limit notation. And here, for us, we're assuming that s is a real variable. We call this k of st, that function in the integral, is called the kernel. Of the transform. For the Laplace transform, k of st equals e to the minus st. That's the kernel of our transform. All right, so let's define the Laplace transform. We've kind of danced around it here, introduced the idea. So our definition. So we're going to say f is defined on 0 to infinity, and capital F is defined by f of s equals the integral from 0 to infinity of e to the minus st f of t dt. This is the Laplace transform. F of s is the Laplace transform of f of t. And the domain of f of s is all the values of s for which the integral converges. And we also write that the Laplace transform we write as L of f of t. A nice script L. So usually we use lowercase letters for our functions of our original variables and uppercase letters for our transforms. So the Laplace transform of f of t is going to be capital F of s. The Laplace transform of g of t is capital G of s, etc. In general, s can be complex in this integral. And we can think of the Laplace transform as a transform from the time domain, t, to the frequency domain, s. And the benefit is that derivatives and integrals, when we transform derivatives and integrals, we end up with multiplication and division instead of derivatives and integrals. So it's kind of like logarithms, where we take a more complicated operation, a derivative, and we turn it into a simpler operation. So big picture, what we end up doing with the Laplace transform is we apply the Laplace transform to a differential equation, and it becomes an algebraic equation. We solve the algebraic equation, get a solution in terms of s, and then we find the inverse transform to transform back to the t domain. So big picture, that's what we're looking at. Why is this better or different than doing the way we've done before? The Laplace transform lets us handle a lot of different kinds of functions that make our differential equation non-homogeneous. So where we have our sums of our derivatives equals g of t, we had some limitations on what g of t could be to apply the methods that we did before. Here we end up with a much broader types of functions that can be our driving functions for our differential equations. All right, so we're going to, this very first section is really just a practice with the definition of the Laplace transform. In general, we don't really have to use the definition. We don't have to do this integral every time because there are tables of Laplace transforms where lots and lots of functions the Laplace transforms have been found for lots of different kinds of functions, and usually we look them up. But we're going to practice with the definition because for some types of functions we do need to use a definition, and using the definition is going to give us some insights into how the Laplace transform behaves, and also why the values in those tables take on the values that they do. All right, questions so far? Okay. Let's look at some examples. We're going to apply the definition. We want to find, I'm going to say find using the definition of the Laplace transform of 1. Well, L of 1 is going to be the integral from 0 to infinity of e to the minus st times 1 dt. So that's going to be the limit as b approaches infinity, integral from 0 to b of e to the minus st dt, which is the limit as b approaches infinity of negative 1 over s. We're integrating with respect to t. E to the minus st evaluated on 0 to b. And I'm going to write this out. Usually we can just, from here, we can evaluate this. I'm going to write it out explicitly. That's the limit as b approaches infinity of negative e to the minus sb over s minus negative 1 over s. We plug in b and 0. Well, this first limit, if s is positive, this first limit is 0 because we have this e to the minus sb in the denominator. So we end up with 1 over s for s greater than 0. If s is less than 0, the integral diverges and the Laplace transform doesn't exist. So this says that f of 1 is 1 over s for s greater than 0. All right, questions there? Okay, let's find the Laplace transform of t now. Laplace transform of t is the integral from 0 to infinity e to the minus st t dt. We need to do integration by parts here. I'm going to write out my little things here. U is t, du is dt, dv is e to the minus st, and v is negative 1 over s e to the minus st. So this equals the limit as b approaches infinity of u times v. So that's minus t over s e to the minus st, and that's evaluated on 0 to b, minus the integral of v du. So that's 0 to infinity of negative 1 over s e to the minus st dt. Well, this first limit is 0 if s is positive, because our e to the minus st, e to the st is in the denominator. So we get that approaching infinity minus t e to the minus st at 0. So that approaches 0 if s is greater than 0. And this second integral is plus 1 over s. Well, we evaluated this one here times 1 over s. We evaluated this integral in the previous integral. So L of t is 1 over s squared for s greater than 0, because we need this integral and the first the limit here as b approaches infinity. For that to go to 0, we need s to be greater than 0. And in general, this is kind of how we build up these tables of Laplace transforms. We find a few simple ones, and then those show up again as we are evaluating more complicated Laplace transforms. So it's kind of a build on previous ones. All right, questions there? Let's look at another one. Laplace transform of e to the at. So that's going to be the integral from 0 to infinity, e to the minus st, e to the at dt, which I'm going to write as the integral from 0 to infinity of e to the a minus s t dt. And just so it's easier to see our convergence, conditions for our convergence when we evaluate this integral. I'm going to write this as the integral from 0 to infinity of e to the minus s minus a t dt, just to make that exponential negative. So this is going to be the limit as b approaches infinity of negative 1 over s minus a e to the minus s minus a t, and we're evaluating that on 0 to b. And this is going to be the limit as b approaches infinity of negative 1 over s minus a e to the minus s minus a b minus 1. This limit as b approaches infinity is going to go to 0 if s minus a is greater than 0. So we get negative s minus a times negative 1. So we get 1 over s minus a for s minus a greater than 0. And that tells s has to be greater than a. So the Laplace transform of e to the at is 1 over s minus a. And so we've transformed an algebraic function, or sorry, an exponential function into a nice rational function, an algebraic function. All right, questions there? Okay, let's look at one a little more complicated one. The Laplace transform of cosine of at. So that's going to be the integral from 0 to infinity e to the minus st times cosine of at dt. All right, we need to integrate by parts here. And we might remember, if we think back to doing integration by parts on a function like this, we might remember what happens here. So kind of preparing in our minds for that. Integration by parts, I'm going to let u equal cosine at. So du is negative a sine at. Didn't leave myself very much room here. dv is e to the minus st, and v is negative 1 over s e to the minus st. So for our integration by parts, this is going to equal u times v, and this is the limit as b approaches infinity of u times v, negative 1 over s, e to the minus st cosine at, and we're evaluating that on 0 to b, minus the integral of v du. So that's going to be a over s, and that's 0 to infinity, of e to the minus st sine of at dt. Well, this comes out to be at b, at limit as b as we approach infinity, if s is positive. This gives us 0 minus, we plug in 0, this becomes 1, this becomes 1, and we get a minus 1 over s, minus a over s integral from 0 to infinity of e to the minus st sine at dt. So we have this factor of 1 over s here, this term 1 over s in front, and then we have to evaluate this integral now. So now we need to do another integration by parts. So I'm just going to look at this integral. For this integral, u is sine of at, du is a cosine at, dv is e to the minus st, and b is negative 1 over s e to the minus st. So we have, I'm going to start out here. We have 1 over s minus a over s times u times v, and this is the limit as b approaches infinity of u times v minus 1 over s e to the minus st. What do we have? Sine of at. And we're evaluating that on 0 to b. Minus, and this is inside the parentheses here, u dv. 0 to infinity of negative 1 over s e to the minus st sorry, v du times, what do I have, an a here? A over s from here, cosine at dt. Equals, I'm keeping careful track of all of this stuff, a over s. This limit, as b approaches infinity, this e to the minus st term gives us a 0 limit, and the sine of 0 is 0. So we get 0 plus a over s integral from 0 to infinity of e to the minus st cosine at dt. Well, this integral is the Laplace transform of cosine of at. So we have the Laplace transform of cosine of at equals 1 over s minus a squared over s squared times the Laplace transform of cosine of at. So now I have an equation that I can solve for the Laplace transform of cosine of at. I'm going to add this term to both sides. So I get 1 plus a squared over s squared times the Laplace transform of cosine of at equals 1 over s. And I'm going to write this as s squared plus a squared over s squared, get a common denominator. So the Laplace transform of cosine of at equals 1 over s times, well, I'm dividing here, so I get s squared over a squared plus s squared when I divide by s squared plus a squared over s squared, which equals s times s squared over a squared. So just to condense this, Laplace transform cosine of at equals s over s squared plus a squared. So several integration by parts there, and we get that result. Anyone want to guess what the Laplace transform of sine of at is? It turns out to be a over s squared plus a squared. But you go through the same process to find the Laplace transform of cosine of at. Or sorry, sine of at. And again, thankfully, we don't have to apply this, the definition over and over and over again. Tables of Laplace transforms have been developed, and in general, we can use a table. Sometimes we have to manipulate the function that we have to get it in the form of something that we can find the Laplace transform of. But once we do that, we can use a table. All right. Last thing for today, I want to talk about linearity. The fact that the Laplace transform is a linear transform is a very nice thing. So we're going to say f and g possess, is it two s's? No, one s. The Laplace transforms f of s and g of s. The Laplace transform of alpha of f of t plus beta times g of t is alpha Laplace transform of f of t plus beta times the Laplace transform of g of t equals alpha f of s plus beta g of s. And we can apply this, we can use this for any number of terms that we have. So the Laplace transform of a sum is the sum of the Laplace transforms. So for example, we want to find the Laplace transform of 3 minus 7t. Well, this is going to be the Laplace transform of 3 minus the Laplace transform of 7t. My braces here are not looking great. There we go. That looked okay. Which is 3 Laplace transform of 1 minus 7 Laplace transform of t, which we've already found. So that's going to be 3 over s minus 7 over s squared. Now often, just as a little heads up here, when we start talking about inverse transforms. So let me back up here. For all of these transforms that we found, what this implies is the inverse transform of s over s squared plus a squared is cosine of at. The inverse transform of 1 over s minus a is e to the at. The inverse transform of 1 over s squared is t. The inverse transform of 1 over s is 1. So you might imagine that sometimes, often in application, rather than this, we would have something like s squared, 3s squared minus 7s over s cubed. And then we have to rearrange that somehow so that we could look these two terms up in our table of Laplace transforms. So we end up with rational functions. We have to separate into individual fractions. We know a process for doing that. Partial fractions shows up frequently when we talk about Laplace transforms because we want to take Laplace transforms of individual terms, and a lot of times this function of s is going to be one giant term that we have to break apart into individual pieces where we can find the inverse transforms.
No, I was like, that's not, it's over.
So what I'm going to say, we won't have to worry about this here. We'll talk about inverse transforms on block day. When you're doing your homework, I would suggest you use a calculator, use some kind of technology to do your partial fractions. Otherwise, you're going to be spending way too much time doing that and not doing the Laplace transform stuff. But like I said, for the last unit, you should be able to make sure you're able to do all of those partial fractions, decompositions for the various things, because I will ask you to do one, at least, on a quiz or test. Yes. Let's do one more example, just because this one's fun. Find the Laplace transform of cosh t. Any ideas what we might want to do here? What's that? Yeah, we're going to write it as our exponential definition. So this is going to be e to the t plus e to the minus t all over 2. So we're going to have 1/2 the Laplace transform of e to the t plus 1/2 the Laplace transform of e to the minus t. Easy. So that's 1/2 1 over s minus 1 plus 1 over s plus 1. Oops, parentheses. And we could write that as s over s squared minus 1. And if we go back to our cosine Laplace transform, s over s squared plus a squared. If this were cosh at, this would be s over s squared minus a squared. So that plus minus kind of very similar between the derivatives of our trig functions and our hyperbolic trig functions. Same kind of relationships here. Because we're integrating, so it kind of makes sense. So we do a bunch of these simple ones. We combine these into more complicated functions, and that's how we build up a table of Laplace transforms. Some basic Laplace transforms. One part of your homework assignment asks you to use the definition, and then the other asks you to use theorem 7.11. Which is a table of basic transforms. And this is on page 289 of our textbook in chapter 7. But what I'm going to say, I think we will define a transform. So the inverse transform of 7 is 16. So that's why we're in chapter 16. I guess, yeah, we could say, yeah, the inverse transform of 7 is 16, so we're transforming that into chapter 16. So that's why the book lists all of these problems in chapter 7, but we're going to call it chapter 16 because we'll have all of our units then will have powers of 2. All right, and our homework. Yeah, the fact that they erased my boards, I had all this stuff written on the board. Oh, and I need to put, I'll put the homework calendar up on Schoology. I have it ready, I just haven't published it. These are from the definition. These are using the table on page 289. And then number 51 and 53. And let me make sure that I wanted 11 through 17 odd and not all of those. So give me just a second here.